Yeah, hi people. So in this part, we will be talking about consistent hashing. So consistent hashing is a technique used in distributive computing systems to distribute data among multiple nodes in a consistent and efficient way. It addresses the problem of distributing data evenly across a set of nodes in a distributed system while minimizing the impact of node failures or addition on the distribution of data. So we can start with the rehashing problem. So for this, let's suppose we have n cache servers, right? A common way to balance the load is to use the following hash method. Like, let's suppose we have 8 servers and each server is having certain hash key. Then basically we will divide these 8 servers with mod of n, where n is the size of server pool. So if our server pool is of size 4, then we can divide mod 4. So based on this, based on these, we will able to distribute based on the number we got. We will be able to distribute our load to the corresponding server. Like for on the first we got 1, so we will be sending our request to one server, and in this we got 0, so we will send in the request to the 0th server. And this way, in 2 we will be sending the request to the 2th server, the 2nd server also. So in this way we can use this hash function to basically send the request to the corresponding server. And when we are fetching also, to fetch the server where the key is stored, we can perform this modulation operation using this hash function. For instance, hash key of a key 0 will, like if I'm doing hash function on this, then it will give me 1. So I know like I can fetch the data from the one server with number 1. Means that client must contact server 1 to fetch the cached data. So in this way, we can use hash function to achieve this. So you see, like we have this server in this hash mod 4 function, and we have these 4 servers labeled from 0 to 3, and based on the hash map we were able to map like this key 1 and key 3, like on doing mod of them we got 0, right? So we mapped them to server 0, and similarly key 0 and key 4 has are mapped to server number 1, and key 2 and key 6 are mapped to server number 2, and key 5 and key 7 are mapped to server number 3 based on the hash value they got from this. Now this approach works well when the size of server pool is fixed, like the size is 4. Then this approach works well when the size is fixed and the data distribution is even. Okay, but however, the problem arises when the new servers are added or existing servers are removed, right? For example, if server 1 goes offline in this, like in this example, suppose server 1 goes offline, then the size of pool will become 3 instead of 4, right? Then using the same hash function, we get the same hash value for a key. By applying modular operation gives us a different server index because the number of servers is reduced by 1. So now, since the servers has been reduced by to 3, then our hash function, we will be changing our hash function to basically mod of 3, right? Because 1 is no longer serving us. 1 has gone down, server 1 has gone down. So now if we use this hash function to get the value, so we see now key 0 has been mapped to 0, which was this 1 has got down, and key 1 is also mapped to 0, right? And key 1 was previously mapped to 0, but, and key 2 is key 2 which was previously mapped to 2 is now mapped to 1. So that also we have to reshuffle because of this new hash function, as the mod has now changed from 4 to 3. Because of a single server change, most of our hashes are now mapped to different servers. That is a problem here. So most keys are now ACC distributed, not just the ones original stored in the offline server. Like not just the keys which were been pointed to this server 1 which has gone offline. Other keys are also are getting affected. Like other keys are also going to now different servers. So the whole redistribution has happened because of just one server going down. This means that when one server goes offline, we can say most cache clients will connect to wrong servers to fetch the data, right? Because wrong servers or different servers to fetch the data. So this causes a storm of cache miss. Consistent hashing is an effective technique to mitigate this problem. And to solve this rehashing problem, when any server goes offline or online, consistent hashing is an effective way. We would be talking about how consistent hashing works and how we can use it to basically mitigate that rehashing problem that we saw previously. So consistent hashing, if we define it, then it is a special kind of hashing such that when a hash table is resized and consistent hashing is used, then only k and keys need to be remapped on an average, where k is the number of keys and n is the number of slots. So k by n keys only needs to be remapped. In here, we just have to remap k by n keys, where the k is the number of total keys and n is the number of slots. Right. So for that, let's just first understand what is hash space and hash ring. So we know what consistent hashing means. So let's assume like we have a hash function and the output range from x, y, z. So like you see this hash space is as of now a linear space which has all the values from x to z, basically from that range between 0 to 2 to the power 160 or so, like whatever range is there. But if we will connect both the ends, then it will form a hash ring. Okay, so in this way we can form the hash ring of the by joining the two ends of a hash space. Okay. Now talking about the hash servers, using the same hash function, we map server based on server IP or name onto the ring, right? Using the same hash function that we used previously, we can map our basically we can map our servers to this hash ring now. So we can see like this is our hash ring, and we have these three servers with us, like server 0, server 1, server 2, and server 3, right? Now let's talk about hash key. So one thing worth mentioning is that the hash function used here is different from the one in the rehashing problem. Like here we are using a different hash function, and there's no modular operation required here. So as shown in the diagrams, the catch keys we have here are key 0, key 1, key 2, and key 3, right? From k0 to k3 hash keys are there with us, right? So you see we have now also placed these cache keys between on our hashing. Like you see k0 is lying between s3 and s0, then the k1 is lying between s0 and s1 on the hashing, and then k2 is lying between s1 and s2 on the hashing, and k3 is lying between s2 and s3 on the hashing. So we have four servers from S0 to S3 and four keys from K0 to K3. Now, if we talk about server lookup, then to basically determine which server key is stored on, and to that is basically to determine which server key is stored on which server, we go in a clockwise from the key position on the ring until the server is found. To find out where K0 is stored, we can go clockwise, and on going clockwise, we can find like S0 is coming, right? So K0 going clockwise, we can say K0 is stored on server 0. And for similarly going clockwise from K1, we can say like K1 is stored on server 1. And similarly going clockwise for K2, we can say K2 is stored on server 2. And similarly going clockwise from K3, we can say K3 is stored on server 3, right? Now, so in this way, how server lookup works on a hashing, right? Now let's just try to add a server to our hashing. So using the logic described above, adding a new server will only require redistribution of a fraction of keys, not all keys that we saw. That was a problem in the rehashing approach. Here we just have to distribute a few keys. Let's see how that happens. So in the diagram, as we see, after a new server 4 is added, like till now we have from server 0 to server 3. Now we have added server 4 too, and we added this server 4 between server 3 and server 0, right? After server 3, we added this. Like in the ring, if we will see, it is added between server 3 and server 0. Server 4 is added. And then we can see only key 0 needs to be, so after adding server 4, we can see only key 0 needs to be redistributed, and K1 and K1 and K2 and K3 remains on the same server. And why K0 has been distributed? Because now the server 4 has been added just after K0 between S3 and S0. So now if we go clockwise from K0 key, then we will find server 4 first instead of server 0. So that means we just have to redistribute or remap this key 0 to server 4. Just all other keys like K1, K2, and K3 are still mapping to the same server. So there is no need to distribute that key. Only just a single key distribution is required on addition of a new server. So that is a benefit here. So now key0 will be stored on server 4 because server 4 is the first server it encounters by going clockwise from K0 position on the end. The other keys are not redistributed based on the consistent hashing algorithm. Now let's try to, like we saw the addition part, now let's try to remove a server. So now when a server is removed, only a small fraction of key requires redistribution with the consistent hashing, right? Okay, so like here we see like we try to remove, as in the diagram we can see we try to remove the server 1 from our hashing. So previously only K1 was mapped into server 1, but now since server 1 has moved, so the next clockwise server for this would be S2. So here also only K1 is remapped to S2 because server 1 has got down, and the next clockwise server is S2 on the hashing. But the K2 was previously also pointing to S2 and will still point to S2, and K3 is also pointing to the same server 3, and K0 will also keep on pointing on the server 0. Like in this example, we have assuming like we only have only have four server 0 to server 3. We have not considered server 4 that we had before. We are just assuming like suppose we had four servers from server 0 to server 3, and our server 1 got down. So now we are only left with three servers. So now the K1 key which was pointing to server 1 will now point to server 2. Only this change will happen. Rest all other keys will remain constant. Rest all of the keys are unaffected when we remove a server. So this is how a basic approach of consistent hashing works, where we use a ring to basically map a server, and whenever we add a new server, then also just a single key, whichever just I think a single key might be a single or a few keys might be required to remap. Not all the keys will get remapped. And in the same happens when we remove a server, just a single or a few keys are required to be remapped. Not all other keys will still remain as is and will be point to the same server only. In this way, consistent hashing can help us here. So the basic approach that we saw for consistent hashing so far has two problems. So the basic steps are like map servers and keys on the ring using an informally distributed hash function. So before discussing those problems, let's just call out the basic steps that we do while this. Like basically, we map servers and key onto a ring. The basic steps that we do while doing consistent hashing are like we basically map servers and keys on the ring using a uniformly distributed hash function, and to find out which server keys mapped to go clockwise from and to find out which server a particular key is mapped, we can simply go clockwise from the key position until the first server on the ring is found. In this way, we do consistent hashing. Now, two problems that I identified with this approach are: first, it is impossible to keep the same size of partition on the ring for all servers, considering a server can be added or removed. Right? Like it is impossible to keep the same size of all the partitions on the ring for all servers, considering a server can be added or removed. Like initially we evenly distributed all the servers, right? But like initially we distributed evenly servers on the ring, but if we keep on adding servers, then that uniformly distribution or the gap between the two servers will increase or decrease based on the addition and removal of the servers also. So we can't always even have a evenly distributed or evenly spaced servers on the ring. And it is also a possibility that the size of the partition on the ring assigned to each server is very small or fairly large, as we saw based on the addition and addition. So here also in the diagram we can see we have our four servers 0, 1, 2, and 3. And now if server 1 is removed, then server 2 partition highlighted with that highlighted with that this arrow, right? Like from server 2 to server 0, since server 1 has removed, this area has become twice the area it was before. Like previously, since server 1 was there, it was occupying only this much area, but now server 1 has gone. Now so the server 2 is occupying this much area. Like we're talking about clockwise, right? So if any key placed from this to this area will always point to server 2. So you see, like if we are placing, since we have more space here, so if we place more lots of keys here, then all will start pointing to server 2. So like server 2 has occupying a larger area because the server 1 has gone down. Okay. And now the second problem with this approach is like it is possible to have a non-uniform key distribution on the ring. For instance, if servers are mapped to positions listed in the diagram, so most of the server keys here are appearing to be stored on server 2. Yeah, right? Because server 1 has been demapped, and here we see server, like all these keys are pointing to server 2, and no keys pointing to server 3, and this single key is pointing to server 2. Yeah. So second, it's possible to have a non-uniform key distribution on ring. For instance, if servers are mapped to position in this diagram, most of the keys are stored to server 2. However, server 1 and here you see server 1 does not have any data, and server 3 is also not having any data. That is also a possibility. So basically, the two problems here like is one, if the server goes down, then suddenly a certain server is occupying very large space, and so we can say these servers are not uniformly distributed on this server. And the second problem is like we cannot ensure like the keys are evenly distributed. It might be a case like the more number of keys are pointing to single server on the ring, and few servers might not have any keys. So that is also a possibility. So these are the two problems in the current consistent hashing approach that we are using. In this part, we would be talking about virtual nodes. So virtual nodes refers to real node, and each server is represented by multiple virtual nodes. nodes on the ring. So both server 0 and server 1 have 3 virtual nodes. Okay, and then the 3 is arbitrarily chosen. And in real world system, the number of virtual node is much larger. So in this, basically, we divide a server into multiple virtual nodes. Like for server 0, we have divided it into server 0 of 0, which is one virtual node, then server 0 of 2, and then there's server 0 of 1. So all these are virtual nodes of server 0. And then server 1 is also divided into 3 nodes. Let us server 1 0, server 1 1, and server 1 2. So in this way, we present our 7 different virtual nodes. Virtual nodes with so here we have chosen 3 arbitrary nodes for each server. In real world system, the number of virtual nodes can be much larger too. So with virtual nodes in each server is responsible for. So with the help of these virtual nodes in each server, we can have multiple partitions, right? The partitions with the label S0 are managed by server 0. So you see, like now because of this virtual nodes, server Z, each server has now multiple partitions. Like all the keys lying in this region, if we'll see clockwise, will point to server 0 of 0. So that will be a part of server 0 only. And here also, these keys will also be a part of server 0 only, as they are pointing to clockwise to server 0 1. And these keys will also be a part of server 0 2 because server 0, because they are pointing to server 0 2. So in this way, we are able to spread out the area occupied by server 0 by dividing it into multiple virtual nodes. And in the same way, we are doing it for server 1. Like server 1 has first this area, has all the nodes clockwise pointing to server 1 underscore 0. And then the server 1 has this area, as all the nodes lying in this region will clockwise point to server 1 underscore 1. And then the server 1 has this region 2, as all the nodes pointing in lying in this region will clockwise point to server 1 underscore 2. So this will also be the part of server 1. So in this way, again, we have spread out server 1 in multiple regions because of introducing these virtual nodes. So to find which server key is stored. So now to find which server key is stored on, we go clockwise from the key location and find the first virtual node encountered on the ring. And to find out okay, so like here we see key K0, right? So the first clockwise node that point where the clockwise server for this K0 is server 1. Server 1 K0 now lies in server 1. So K0 is stored, we go clockwise from the location and find virtual node S1, which refers to server 1. Yeah, that's fine. So as the number of virtual nodes increases, the distribution of keys becomes more balanced. Like if server 1 goes down, then it will point to server 0. But by introducing these virtual nodes, we're able to balance out things in a more better way. The distribution of key becomes more balanced now. This is because the standard deviation gets smaller with more virtual nodes, right? Leading to the balanced data distribution. And standard deviation measures how data are spread out. The outcome of an experiment carried out by an online research shows that with one or 200 virtual nodes, the standard deviation is between 5% only now with 200 virtual nodes, and 10% with 100 virtual nodes. So you see, with them as we go on increasing the virtual nodes, the standard deviation will reduce, and basically we will be able to balance out our traffic in a more better way. The standard deviation will be smaller when we increase the number of virtual nodes. However, more spaces are needed to store the data about virtual nodes. That is one trade-off we have to make. This trade-off, and we can tune the number of virtual nodes to fit our system requirements. So one way to basically improve our approach is to basically reduce multiple virtual nodes, and that will try to balance out traffics. And like even if server goes up and down, we are still able to balance out things across these virtual nodes also. One way is this, to basically have a more uniformly distributed load across different servers. So in this part, we will talk about finding affected keys. So when a server is added or removed, a fraction of data needs to be redistributed. So how can we find the effective range to redistribute the keys? Okay, so that is a concern here. Now, if we see the diagram, in this server 4 is newly added to this hash ring. So the effective range, since the newly S4 server is added, right? Then what we can do is, now the S4 is added. Now we can move anti-clockwise around the ring until a server is found. From S4, we can move anti-clockwise on the hash ring until the server is found, and which in this case is S3. Thus, the keys located between this S3 and S4 will now be redistributed to S4. S4, right? Because S4 is the clockwise next server for all the keys lying between S3 and S4, right? So they will be remapped to the server or redistributed to the server S4. So in this way, we can handle the addition of server to our consistent hashing ring. Now, if we talk about the removal of server. So here we can assume like we here we can say like we are if you see the diagram, we are now removing the S1 server from our hashing, and now only three servers will remain after removing S1, that is S0, S2, and S3. So now what we can do is we can look for all the keys that are located between S1 and S0. Like we can anti-clockwise move to S0 and C and just take the record of all the keys that are between S1 and S0, and then we will redistribute these keys to the next server after S1, which is S2. So in this way, we will remap all the keys between S0 to S1 to S2 via anti-clockwise checking it and then mapping it to S2. So in this way, we can handle the scenario when keys are being removed for our consistent hashing ring. So yeah, that is pretty much the way of finding the effective keys and redistributing them to their new servers. But we would be summarizing consistent hashing. So we can start with the benefits. So the benefits are consistent hashing redistributes minimized keys when the servers are added or removed. Like on the contrary to the rehashing technique, in the consistent hashing, we can only remap the keys which are for the newly added or for the newly added or already removed or existing server removal also. We only redistribute those keys instead in the case of rehashing where we redistribute all the keys. So one benefit is that. Then the second benefit it allows for easy horizontal scaling by evenly distributing the data. Okay. And then it mitigates the problem of hotspots where excessive access to a specific shard could cause server overload. Here, these hotspot generally happens because of that celebrity problem that states that, like, suppose few shards are having the data of the most prominent persons, or like if you're talking about any social network, let's suppose Twitter or so. So suppose a particular shard is having the data of all the popular celebrities like Justin Bieber, Miley Cyrus, or like basically all the popular people are being stored in that shard. Then there will be lots of requests to that particular shard, and that will act as a hotspot, and then the load will increase on that. So basically, using the consistent hashing way, we can mitigate this problem where we can basically where excessive access to specific shard could, like, we can mitigate this problem by using the consistent hashing way also. So that is one more benefit of it. Then the last benefit would be like consistent hashing distributes the data more evenly to prevent hotspots. Yeah, that we saw, like, since we are using we are creating ring and we are evenly distributing the data across different servers by also implementing that virtual nodes in place. So we are able to evenly distribute our data and avoid the scenario of causing any hotspot or so. Now, application of this consistent hashing approach. It has a wide variety of application, and it is being used by lots of internet companies. So we can start by Amazon's DynamoDB, which uses consistent hashing as a partitioning component to distribute their data across its database. Okay. And then Apache Cassandra leverages consistent hashing to partition data across its cluster. Okay. And then the very popular chatting platform called Discord also employs consistent hashing for efficient data partitioning across its database systems. And then the Akamai Content Delivery Network. Then the Akamai Content Delivery Network also utilizes consistent hashing to distribute the content across multiple servers. So, and the last one more application that we can see is that Maglev Network Load Balancer also uses consistent hashing for efficient distribution of traffic among multiple servers. Yeah, so that is pretty much on the summary part of consistent hashing.